The function that we're looking at here is read as y equals 3 to the x power, and it's called an exponential function. And an exponential function is written in the form y equals a times b to the x power. And there are two rules that an exponential function has to follow in order to be considered an exponential function. Rule number one is a cannot be 0. And rule number two is that b cannot be 1. So as long as a is not equal to 0 and b is not equal to 1, and also b has got to be bigger than 0. So b is going to be a number that is greater than 0 but not 1, so b could be a fraction, and a can't be 0. So for example, an exponential function could be y equals 2 times 4 to the x power. That'd be okay. A isn't 0, b is bigger than 0 but not 1. But we could also have one where it was like, let's say 3 times 1/2. I'll use parentheses there so it's a little easier to read. 1/2 to the x power. That's also an example of an exponential function. B is bigger than 0 but not 1. B is less than 1, but that's okay. It can be. It just has to be not 1. It can be lower than 1. And we could also do something like negative 4 to the x power. And you might be thinking, wait a second, hold on, you said b has to be bigger than 0. This is negative 4, right? No, this is the same thing as negative 1 times 4 to the x power. That is an exponential function. That's okay. What would not be okay is for me to do this. That is not exponential because now my b is a negative number. I'm doing negative 4 to the x power, so that one's not exponential. Okay, so those are the basic rules. A can't be 0, b has to be bigger than 0, and b can't be 1. And then x is going to be our exponent here. So we've got y equals 3 to the x power. And what we're going to do with this exponential function is that we're going to graph it. We're going to find the y-intercept, and then we're going to talk about the domain and the range. And so there's a few ways to graph it. One way that we can graph it is we can make an xy table. We can just pick some values of x, substitute them in, and find the corresponding values of y. And when we do this, I like to get a couple of negative x's, a couple of positive x's, and 0. So we'll like -2, -1, 0, 1, and 2. So then our y values, let's start off with 0 and the positives. 3 to the 0 power is 1. So our first coordinate would be 0, 1. If x was 1, we would have 3 to the first power, which is 3. So our next coordinate would be 1, 3. And then if x was 2, we would have 3 squared, which is 9. So then our coordinate after that would be 2, 9, like so. The negative x's are going to give us, of course, a negative exponent, and we've learned how to deal with those previously. 3 to the -2 power is the same thing as 1 over 3 to the +2 power, which is 1/9. So this coordinate would be -2, 1/9. And then something similar with the -1 exponent. It would be 3 to the -1st power, which is 1 over 3 to the +1st power, which is 1/3. So this coordinate is going to be -1, 1/3. And so you'll notice a couple of things. The first is that no matter what we plug in for our x value, we always get a positive y value. And the other thing you'll notice is that although the y values continue to get smaller, 1/3, 1/9, if we plugged in -3, we'd get 1/27th. Although the y values are getting smaller, it's hard to think of an x value that would give us a y value of 0. And in fact, if we go to a graphing calculator, and let's go ahead and do that right now. Let's go to a graphing calculator. Let's go to y equals, and let's put in 3 to the x power. And let's go look at our table. So let's do second graph. And here's our table. And there's our first couple, 1, 3, 9. Of course, there's 27. And if we go back into the negatives, 0.333, of course, is our 1/3. 0.111 is our 1/9. And as we get into our negative exponents, there's scientific notation because the fractions are so small, but they're still positive. 3e negative 10 is a very, very tiny number, but it's still a positive number. And in fact, no matter how low we go, we get smaller and smaller and smaller numbers in scientific notation, but those numbers are still positive. And this is important to us whenever we're talking about our exponential functions. It means that no matter what we put in for our x, no matter how low our x value is, our y is always going to be positive. Well, what's that going to look like when we graph it? Let's go ahead and press the graph button and see. So here's a graph of our exponential function. And what I want you to notice is that the graph, as we go to the right, as our x value gets bigger, increases very, very quickly. This is called an exponential growth function. It increases extremely quickly. As we go to the left, though, it flattens out. It gets really, really, really close to the x-axis. Looks like it's practically touching the x-axis. But as we know from looking at our table, it doesn't actually touch the x-axis. It gets really, really close, but doesn't ever actually touch it because the y value never becomes 0. No matter how far we scroll, no matter how low the numbers get, and the numbers get very, very, very low, we never hit 0. The calculator actually will eventually show us 0, but that's because the numbers in scientific notation get so small that the calculator can't show them to us anymore. Once we hit negative 99, the calculator can't calculate digits any smaller, and then it shows 0. That's not because the function actually equals 0, it's just because the calculator overflows and can't show us a number that small. We've reached the limit of what the calculator can do. So if we were to graph this, we would have an x-axis and a y-axis, and what our graph would look like is something like this. Our y-intercept, of course, is this coordinate right here, 0, 1. That's our y-intercept, so right here at 0, 1. And our domain is all values of x. X we can go as low as we want to and as high as we want to on the x-axis. So the domain is all real numbers. Or if you wanted to use a different kind of notation, you could say x goes from negative infinity to positive infinity. The range, on the other hand, is limited. Although we can go up as high as we want to, this will go up forever, it doesn't go down forever. It gets really, 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 really close to the x-axis, but will never actually hit 0. So the range is that y is greater than 0. It almost touches 0. Almost, but no matter how small of an x value we pick, it will never actually touch 0. There's an invisible line right here. An invisible line that is keeping that function from dropping lower than that. It's almost like a barrier right there that the function cannot go below. And that barrier has a special name. It is called an asymptote. Isn't that a funny name? It's called an asymptote. And the asymptote is that invisible barrier that the line cannot go below. And for this problem, the asymptote is y equals 0. The line cannot go below, or the function, I shouldn't say line because it's not a line, it's a curve. The function cannot pass below y equals 0. That's what an asymptote is. It's like this invisible barrier, and the function can't go lower than that. So this is how you graph an exponential function. The domain is all real numbers. The range for this one was y is greater than 0 because it had an asymptote at y equals 0. That's not always where the asymptote of an exponential function is, and we'll look at some examples in a little bit that do not have an asymptote at y equals 0. But the range for an exponential function is always going to be limited because at some point an exponential function is always going to flatten out. There's always going to be a point where it flattens out and does not pass above or below a certain point, and that point is called an asymptote.